Yeah, so what we're going to be talking today is about our software, our suite of software for gas modeling. So we are going to give you a very little introduction about our company, HR Wallingford. Both Alex and myself work for this company. And then we will show you very briefly our software portfolio. We want to do this very dynamically, so it's going to be mostly all the time demo. So the introduction will last for 5 minutes. And then what we will have is we've got three software we want to show you. Probigas is our traditional desktop software, so the software you would use for building up your models from scratch. And it's the software that we intend for professional network modelers to use. And then we will pass what I think is the most interesting part. We will show you our Simon software. We've got two, Simon Gas Design and Simon Gas Operation. And the idea is completely different there. They are web applications. And what we're trying to do there is to democratize access of modelings to people that are not professional modelers, so people that they want to benefit from the models, but maybe they don't have the expertise or the time to learn all the complicated things of models. So while we are creating these platforms for them to do simple things in a controlled environment. So Simon Gas Design is basically Probigas in a web environment where you can just do very little modifications in the network and run some cases. The idea is also to have a centralized hub when different teams can be doing approvals, projects, and piling on all these things in the same place. So everybody is considering previous projects done by someone else. And Simon Gas Operation is basically a digital twin. Those models that we've developed, and rather than being on a drawer for many years, we put them live with SCADA data. But again, they can be accessible by people that are not professional modelers and people that might just want to benefit from having those models and see how they work with real-time data. We will get into that later on. Simon Gas Operation is slightly more complex because we got the SCADA data there embedded. So we will spend 20 minutes with that software, and hopefully we will leave 10 minutes at the end of the webinar for questions and answers. And obviously you will have access to our emails. If there is anything that we don't have time to discuss today, we can discuss it any other time. So very briefly to introduce our company, HR Wallingford doesn't have anything to do with human resources. That's a very common misleading name for our company. It's actually hydraulic research. We were created in 1947, more than 75 years ago. We were part of the British government, and this is actually our headquarters in very close to Oxford in the UK. And this is a building from 18 something, very quite old, and this is where our headquarters are. When we got privatized in the 1980s, we were privatized as an independent research organization. So we don't have anyone that owns the company, surprisingly. We need to reinvest all our profits into research. And some of the tools you are going to be seeing today are actually the product of that internal research campaigns that we need to be funding every year with the profits we make with our normal operation. So we are not a charity. We look for a profit. But what we try to do is that then those profits, we reinvest them into research rather than distribute them. And we were basically initially the hydraulic lab for the British government, but we've been shifting over time, and we've been doing many things. And now we are doing basically a lot of things with energy. We do have offices all over the world. One office is in Houston in the US, but we also have offices in the Middle East and in Asia, as you can see in the graph below. If you happen to be in the UK, we are always very, very happy to show our facilities to any visitors from overseas. We've got an incredible hydraulic lab where we do physical model experiments. We've got a ship simulator. So it's a very interesting place to see our headquarters in Wallingford, UK. The software we are going to talk today about are basically three, as we said. Probigas, which is the classic desktop application, like it could be Synergy or like it could be Gaswork. So here you will be working on your desktop and you will be creating your models from scratch. It could be used as a surrogated asset management, but that's not the function we created for. And then what we've done is that technology that we've got for desktop modeling, we've transferred it to a web environment, and we've created Simon Gas Design. So in Simon Gas Design, you can do, again, the same kind of steady state simulations that you were doing in a desktop, but in a control environment where it is easier for the people that are not expert modelers to run simulations, and then to centralize all those results in one single area. And the next logical step was to move that into a live environment where these models that we've created in the desktop application can be actually connected to SCADA data in real time, and we can know what's going on in your system, in your system every moment. And you can also combine with a forecasting tool. We can know what is going to happen in this system. Okay. Then it allows you to do also what if scenario, what happens if I close this valve, and you will see that that's very interesting. To finalize in this quick introduction, just to let you know that this is the way we usually work. Probigas is our base where we create the models, and then we work with Simon Gas Design and Simon Gas Operation, which is in the web environment. But actually, we are also compatible with any other software. So if you use other software and you don't want to move to Probigas, that's not a problem. You could bring into our web platforms your model that you've created in your own platform. Obviously, we would love you to change to our system, but maybe you have other conditionals, like your end client doesn't want to use a different software. So one thing that you could also consider is our technology from Probigas. Maybe it's cheaper than what you are using now, and it could be an interesting way because it allows you also to build the models in that technology and maybe export them to the current package that you are using now. Okay, so if what you see today is interesting for you, we can explain to you how you could be tuning things and working with your environment. So Alex is actually going to show you now. Alex is the head of the development of the software. I'm the global product manager. And so Alex is going to give you now a demo on Probigas. 10 minutes, Alex. So start whenever you want. I stop.
Okay. Thank you, Juan. Now share my screen. And I share the entire screen, and I will demo you Probi first, and following that, I will also demo Simon Design, 10 minutes each roughly, so I'll try to not to go over the time. So this is, I suppose you are seeing my screen. Juan, can please confirm?
Yep, you can see.
So this is the Probigas desktop application. So what is it for? This is a platform software, desktop software, which helps you to bring in data about your gas distribution network, demand, regulator stations, etc. And you can run a simulation and get results. It's quite a simple piece of software, quite logical to use, easy interface. The first thing I would like to show you is the database, which is quite an important concept. In this software, you are not working with files, but you are working with a database. So all your work is secured inside a database structure. So you don't need to save as, you don't need to save files around your hard drive, but it's all centralized and shareable with other users. So typically what you do with this software, you are creating networks like I do now. You're opening your networks, which now is a white page. And you are typically importing asset data. Asset data in gas is pipe, valves, regulators, demand. I show you some functionality on this side. So I'm now, for example, importing some pipes from shape files. I'm specifically interested in diameter, material, and pipe pressure class, which I'm not sure how you call it in the US. Basically, it's the pressure rating of your system. So I press import, and now the software has imported 2,307 pipes, which I confirm I want into the interface. So now Let's have a look at what the result of this operation is. I have a table which all the pipes imported with length automatically. I didn't import length, but it was calculated. I imported the diameter, I imported the material. And if I want to look the layout of the system, this is the layout we imported. Please note the system created nodes automatically. I only imported pipes because the software really needs the connectivity. If it doesn't find nodes already there, it will create it for you automatically and creates the connectivity. I can import other objects, but we have no time really to do the full demo, so I will import another object which is quite classic. Is the customer. Is basically the idea is that we are mapping one by one the users, in which case I'm importing a reference ID and demand. By importing user, what I'm trying to do basically is model very accurately demand distribution in the catchment. Rather than allocating demand and nodes, I'm actually importing the single user, which helps me to attribute very accurately demand around the catchment. I'm not going to have time to show you, but basically these are customers which will then be allocated to pipes. I can also manage, if I remember them, I need to do set a reference system, which I don't remember what it is. I'm just reading from an email. It's 32640. We are in Hawaii here, which is of course a totally fantasy situation. We don't have data for Hawaii, but we are using this. We created this data set ourselves for demoing purpose. So now I have set this system in Hawaii, and I have ability to open background layers like I do now, which is, in fact, this is a web service. So it's not data on my screen, but I'm using a web service. Or I can apply a digital terrain model by simply click and drag. Here it is, which helps me to allocate elevation value for each of the points in my network. Now, elevation has some implication in gas, not as much as water, but you need to take that into account to do model, to allocate a Z value, to provide a Z value for each of the nodes in your system. So this is the interface. It's easy to use. We import data, we manage data. We use this software to, 4 minutes to go, thank you. We use this model to clean data. So we have a number of tracing tools. We can correct mistakes in connectivities. I'm not sure we can kill this. Let's do it. I will now show you the typical results of a simulation. Simulation runs is a compressible fluid. I basically calculate flow, pressures, velocities at each location in the network. Typically, the best way, at least we believe is the best way to look at results, is by observing result class by class. So, for example, now I want to see pressure and velocity on the medium pressure lines. These are pressure in millibars. These are velocities in meters per second. So I'm mapping all the medium pressure pipes, and I display pressure and flow. I can also show another pressure class, like this one is a low pressure system. The pressure range are very different to the one I showed earlier, so we need another team to distinguish. And here is clear, there's an area which is soft or low pressure with this value of 13 millibars delivered at the very end of the system, which is quite low for this type of analysis. So this is a typical steady state simulation. It takes a second to run this sort of size of a network. We can run other type simulations. For example, we can run simulation which helps me to understand how much residual demand I can serve. So how much extra demand I can guarantee to a point in the network without compromising the service in that point or elsewhere. I can run critical link analysis, which is something I can show you briefly. Is a simulation which helps me to understand how important is an element inside your network. So, for example, let's have a look here. This is a network, a switch off node, where this is a thematic about criticality of each object. So it tells me how important is the object in the network. So if I remove this object, this pipe, it's rated 1,869. That means that this sort of amount of customer will suffer critical conditions if this element is out of service. So the simulation goes one by one in the network, removes an element, calculates the effect in the network of that network without this object, and calculates how many customers are out of service. So this mapping will give you an exact idea of what are my critical elements inside my network. And the red are the most critical, meaning that they're out of service, a kind of disaster happens. Whereas in other areas, we have the zero. So this pipe can go out of service with no effects, because gas will be delivered via other loops. I view, for me, this is the more or less what I wanted to talk to you about ProBgas. I now move to Simon design, right, Juan?
Yep, perfect.
Okay, so we have this model now. This software is easy to use, but is for modelers. It's not for operators or sort of low-skilled designers. It still requires some skills. The idea of Simon Design is, let's take this model into another platform, which is extremely easy to use, and is done. This platform was done to help designers. So I take this model and I move it to a web interface, which is this one. When I enter the web interface, I can see all my networks available I can use. I click on one box and the network opens. Now, in this simplified environment, here there's some, you can see some symbols that mean something. In this environment, customers or low-skill engineers can do simple operations, which are dedicated to design activity. Typically, the question would be, what happens if I create additional demand in this node? For example, I create a new project. The software will replicate the data set which I imported from ProB, allows me to create text. And now in this environment, I can do very simple operation using this side menu, such as adding extra demand, splitting a pipe, creating a new pipe, creating a valve, simple operations. So let's, for example, concentrate on this node. In this node, I want to add 10 standard cubic meter per hour extra demand. Now I've added this demand. I run a simulation, and the software will provide me with this result, which compares against the previous state. So the simulation that was run before this one, with including all other design activities by other users. You can see here there are some symbols. Some people already did some work. In this case, it added a node, a pipe was added here, demand was added here. So all is being tracked in this system, because the system works in sort of compiles a number of editing which were done by different person and make them adding all together. So there was a report which I was not able to read, but basically if I now go in here, for example, and I interrogate this node, now the pressure on this node is 23.2 millibar. Before I was running this test, there was another pressure which was higher because of course I added demand, so the pressure went down. And this is the pressure which was imported at the very beginning. So the beauty of the software is easy to use, but it's tracking all the changes so that the company that manages the network can trace what happened in different designs. I'll show you what I mean here. In the history of this network, number one was imported, and there are a number of design tasks which were added by different people, by different users, with different purposes. But the software keeps track of each of these projects and add up the effect. So if I'm running a design now and I approve my design, next time somebody will do another design, my previous design is already taken into account. Of course, I need to run and approve. If I discard my project, nothing happens. So this is the idea. A very easy environment. I can do very simple things. I'll maybe show you other things like cutting a pipe. I want to cut a pipe here. The software will ask me a demand at this node, an elevation on this node, which I now skip. Because maybe I want to serve another big customer at this point. So I'm now adding another node here, which I put as class 7. And I now draw a pipe from this to this. I need to select the pipe diameter out of a list, set the roughness, and that's it. So as you see, my new additions are easy to trace because they have a different thematic. So I've split the pipe here, I added a new pipe here, I add a new node here. So now I can again simulate, save, and commit this changes for the future. Did I, Juan,
you still have 4 minutes if you want to extend on this one.
Okay, so I can show you maybe a bit more details. I can now go here in this point just to make things more realistic. 11.6. So I run now. I'm just setting the elevation right. I'm now putting at this point another elevation and a very heavy demand, like 20, let's say maybe a bigger number. 500, so a very big number of demand, which I expect will be failing my network. So I'm now running my network again. And the result I expect will be quite dramatic because I maybe went overboard with the demand allocation. This pop-up window, which happens, will return in a few seconds, will give me a preview of the results. So it will check if my addition of the network causes problem exactly at the point where I'm adding or elsewhere in the network. Because by adding demand here, I might put into crisis a point maybe is here, because maybe there was the most critical point in the system around this location. You see, I screwed up quite significantly in a number of situations. So this is something I probably will not want to approve. But if I did approve, this addition would be passed on to the future for the further use in further users downstream of my project design. Also, there is maybe worth showing to you.
Can you zoom in to show the themes? Because maybe it's not clear to show the theme of the velocity.
The schematic shows this. The color, the red means the pipe class, so pipes class 7. But this surrounding circle in cyan means that there's a criticality in pressure. This orange background color means there is too high velocity, because every pipe and every node has a minimum pressure and minimum velocity, which should be respected. Sorry, minimum pressure, maximum velocity. So if you go over these parameters, the software will provide you with this warning that something didn't quite work. Perhaps it's worth, maybe I can show you also results. Let's have a look. Where are the results? There we go. So here are the results. Means that every node has pressure, previous pressure, the base pressure. So this is the pressure import in the network. This is the pressure that I started from before my design. Because between this and this, there are other design activities that were carried out. And this is the current pressure in the network. So, for example, here I have a very stupid number because I exaggerated. In this node, there is a minus 20,000, 2,000 millibar, which nonsense number, of course, because I exaggerated. So, for example, here, give me the percentage of decrease in pressure in the network due to my additional demand. So, the beauty of this is simplicity and tracking. Simplicity, I repeat myself, but it's something that I suspect anyone can use with the minimum idea of what a gas distribution network is. And tracking is just the ability to keep a very thorough tracing of how the network changes in different design tasks.
Perfect timing, Alex.
Okay, thank you, Juan. Back over to you again.
So what we've got here is Simon Gas Design. So this is the digital twin. So we do have a landing page where we might have maybe different networks. We click in one of them, and it brings us to the same model that Alex is been using all the time. The particularity here we've got, this is not a design situation. So this is a real time. So we've got some SCADA data. Wherever we've got SCADA data, you can see some triangles in the city gates or in the regulator indicating places where we've got SCADA data that we can feed into the model. Some of this data is going to be used as boundary conditions for the model. Other of this data is going to be used as a calibration data to see whether the model result we are getting makes sense or not. Okay, so I've got an overview here which tells me when was the last time the simulation was run. We've got set it up now for running every hour. It tells me all the gas entering into this system. We've got 2 city gates, so it's summing up the SCADA data for these 2 areas. And then what it's telling me is in each of these medium pressure or low pressure networks, what is the worst case point in terms of pressure. So I can find out what is my most critical point in the network. I don't have any current issues. There is no maximum velocities that we've overcome or lower pressures that we are getting close to. It tells me the volume of gas I've got here. I've set up the demo in PSI units because I knew Alex was going to give you the demo in metric systems. So all the software we've got work with PSI units as well. So we are running it here in that way. And what's the beauty of this? You give me a few sensors and I give you a few SCADA points, and I give you a virtual SCADA system where in each pipe of the module, I can know flow velocity, or in any node of the system, I can know the pressure, okay, and where the gas comes from, for example. So I'm creating a virtual SCADA system just by running a physically based simulation that use some of the data boundary conditions. I can go to some of my charts and look at all those points I am not using as a boundary condition, but I can use as a calibration. For example, this is a point located there where in the regulator, in the governor I've got here, in the incoming pressure of that regulator, I am not forcing the model to follow this pressure, but I am just calculating it, and I can check how well or how bad the model agrees with my data. Okay. This is the current moment, this vertical line. Anything on the left is history. Anything on the right is forecast. The forecast tool here now is not working very well, so we will have, I will show you now, but this is the kind of thing that you can do. So I can go to any element in the model that I've got as a calibration point, and I can identify very easily whether the data I am getting there, well, it makes sense, or whether it's a bit funny. I do have also here all my historical data. Okay, so this is what we were talking before. It is actually a way also to visualize your SCADA data in a simple way, and give access to people also looking at the historical data. Maybe pressure is not the best. I'm going to show you the graph of the total demand of the system. So this is one of the key graphs that we've got here. So if I see the history of my total demand, obviously you can see here the seasonal variation from consumptions in winter and in summer. And also here you can see the temperature. So obviously when the temperature is high, people use less the gas to heating. And I could interrogate any historical period of data to see what's going on in the model. So I've got here a virtual SCADA system that gives me information in any pipe or any regulator or any node on the system. But because I do have a way of estimating the performance of the demand in the future, I am also able to look at things in the future. I'm trying to open a graph here, and it is, I think it's, oh, yeah, sometimes when I'm having presentations, it doesn't like, the internet band doesn't work very well. So I want to show you, so we've got here some forecast behavior on the system. And so what I can do is, if I know how the system is going to be behaving, what I can do is I can move this wheel here, and rather than seeing the existing situation, I can see the future. So it's like I had a virtual SCADA system that also can see in the future. So if I click in any pipe now, I don't see anymore a value only. I see a value and a time. This is the worst case scenario in my forecast. So it's telling me that for that particular pipe, the maximum flow is going to happen at this time at 6 p.m., this date at 6 p.m., and the velocity. And the same with the node. So if I click in any pressure, it will tell me what is the issue. You can see that here we've got some of the nodes colored in a different way. So the system is forecasting some areas where pressures are not going to be or getting very close to the minimum pressure. And in this particular chart, the blue node, this area is telling me that demand had to be suppressed, or will have to be suppressed at this time, okay, at 7 p.m. Obviously, this is a demo, so the dates are just cycles, and they don't agree with the real data. But if we were in a real case, you will see maybe tomorrow's date here, okay? And it's telling me I've got 2 moments in the future where the demand is going to be suppressed in this area because it is actually too low. So that brings us to the third stage of what we can do in our digital twin. So I can run tests, and I can try to change the future to try to do something about those problems. For example, this area, it's the area where we were having problems. I could go to that regulator, and I could try to change the pressure on that regulator. Shall I increase it to 0.4 psi? Would that solve the problem? Well, let's see. I can run here, and I can see run this from 5. Yeah, that's fine. So until 8 o'clock. Okay, so let's run 3 hours. Let's do a bit more until 10 o'clock. Okay, so I am running that. It's popping up with this error message now, but it's actually running because you can see here that this is doing the simulation. So it's running all these future scenarios now with a what if scenario with this change on the network. It has finished to run those 6 hours of simulation. And what you can see now here is all this low pressure in this area have disappeared. But obviously, I didn't touch this area. So these guys here haven't changed, okay? So this is kind of an interesting way in which you dynamically could be operating your network, and you could be modifying settings in case you have some foreseen problems that are happening because of high consumption. The other typical application is, imagine that you need to do some maintenance operation. I'm going to do something really stupid. I'm going to close this regulator, and I'm going to put here bypass. That's going to be a polyethylene bypass. I'm going to make it very small, so 0.5 inches and just 10 feet long. Okay, so I'm closing this regulator. I'm putting a very small bypass here, and I'm going to run the same simulation. Obviously, what is going to happen now is this area is going to have serious problems of pressure, because gas needs to give a big loop to come back to that area. Okay, and so that shows me if I'm doing maintenance operations, for example, in a system, I can try the implication of my maintenance operation, and I can see what is going to be the impact on the system by doing that. Okay, so yeah, so it is calculating. Obviously, we are running 5 hours of simulation. That means 5 simulations. We are actually in this type of simulation, we need to interactively remove customers. This is not anymore like in Simon Design where we were having negative pressures. Here, we don't have negative pressure, while we've got this customer that had been disconnected. And you can see that if I do this maintenance operation, I'm going to let all these people with no gas because they don't have enough pressure. Okay, that could be a maintenance operation that I can refine now, and I can say, oh, maybe I shouldn't put this bypass. Let's do it in 2 steps. I could remove this one and rerun, and I will see that these guys come back to life. Or it could be an emergency. So maybe that pipe actually broke, and I just remove it, and I can see who are the clients that have been affected by that situation. Okay, like it happened in Simon Gas Design, I've got 2 options. I can ignore this change, or I can save it. I'm going to save it. I know it's a stupid change, but let's save it because I want to show you something. So if I save that, now this that it was a kind of like a parallel universe simulation, a what if scenario, now is going to become my future. Okay, so it is realizing I want to do that while we are talking. What the software is going to do is going to rerun this expected simulation. It still hasn't done it. Okay, it hasn't yet gone through, but the software now is recalculating that. And as soon as it does it, we will have a warning here, and it's going to tell us, watch out, because the future has changed. And I'm seeing that because I'm doing it, but anyone else that is using the platform, that could be used by many operators at the same time, they will have the same pop-up message, and then they will know that something has happened. You see, we've got now a warning here. The expected state has changed. So if I click here, I've got an update of what's going on. And now, in my future scenario, this maintenance operation, and also this one I put somewhere here, they appear as part of the future scenario. Okay, so I am aware that this is happening. This is the implication, and obviously this is an extreme case. I am doing something terrific terrible to the network. But if it's a maintenance operation, and I've got 4 or 5 times teams working in parallel, they could be seeing where other guys are doing maintenance operation, and whether they are affecting each other, or whether they are actually working in places that they don't have any interaction. So if I go to any of the charts I was seeing before, what you can see now is a vertical line. It's appearing. We've been unlucky with the color. Usually it's a very colorful band, but today is gray. And it's telling me that there is some some maintenance operation happening from now until 10 p.m. Okay, and any graph of the system that I look at will mark that, because that might have an implication on the results. So you might be seeing the results and not understanding what's going on, and then that will give you this clue on the results. Okay, so basically this is the 3 things we can do. We can look at the network as it is now based on that simulation. We could see in the next few days, you can set it from 1 day to 5 days. Basically, we are forecasting based on two things: the history of the network. So whether we are in a Monday, Tuesday, or weekends, or if it's January or if it is December. So the past history of consumption help us. And then also based on the temperature, because obviously the temperature is going to have an impact in the consumption. And because we don't have very reliable temperature forecast for more than 5 days, the software only allows you to calculate a maximum of 5 days ahead in the future, in the expected scenario. Yeah, we are looking now into maybe making the possibility to run for longer if some clients want to, but we limited initially to 5 days because this is the reliable forecast we've got of temperature when using the software. And to finalize, obviously, every time that there is a new simulation, obviously, you will see these results changing, but you might want to go and see a particular moment in time, maybe when there was a break or something like that. So you click here. What we've got here is the history of all the simulations we've run. We run current states every hour, and we run expected state every 6 hours. So I could go to any of these moments, and I could open that simulation, and I just could see the results at that particular time. So I could go to this. I could go to this regulator, and I could look at what was the results here, and I could see actually at that time. I'm not anymore in the present moment. I am in a different place. This bar where it's telling me when the simulation happened. Okay, so I can also dig out in some of the past simulations. They are all stored there, and I could look at the results in a different moment, not just now. The software has got some fancy things, like you could obviously see satellite image. So again, we say that this is Hawaii, and this is the famous volcano there. I could also connect and track my position. So if I was in a mobile, on a tablet, I could see where I am now. Obviously, it's going to take me to London, where I am now. Okay, so that's useful if you are using the tool on the field and you want to see where you are exactly. So it's got very nice features. And yeah, I think I've showed you almost everything, or everything I wanted to show you about that. It's very easy to use. You could see that actually you would learn how to use it in less than an hour. And then if you're an operator, you don't need to understand very complicated models, how to run them. There is an emergency. Oh, I need to wake up the modeler because it's midnight, and I need to do some simulations. Anyone with access to this tool could be very easily testing different scenarios, running simulation, benefit from the hard work that the engineering team maybe have spent creating those models, and democratizing access to these models, so any operator can learn or can improve his knowledge of the network or understand what's going on. Okay, so I think this is the philosophy of our Simon tools, getting people that don't tend to use models, or maybe don't tend to use SCADA data either, and give them access to this data. And the more the merrier. So this is a web base, so you could have 20 different users looking at the data at the same time and doing tests, and it will cope with that. Okay, so I think that's everything I wanted to show here. Maybe we can come back to the floor.
Hey guys, we do have a question from Clint. He says, are APIs available with Simon for integration to campus or facility twins or digital twins? We do asset management for an airport and are working on ways to make solutions such as yours visible with context other digital twins.
That's a very good question. Actually, yeah, we don't have it yet, but we are actually working with a client in Italy that is asking exactly that. They would like to have access to our results from Simon, so they can be published in their GIS platform that they are creating for our clients. So the short answer is no yet, but we are working on that, and we will have it shortly. Obviously, we think that some of the things we do, like the tests and things like that, maybe it's better to use our platform, so it could be linked via some hyperlinks to our site. But for example, the current state, knowing what is the current flow going through one pipe and understanding the velocity or the pressure in nodes or things like that, that could be requested via API, and it could be edited and published in a different platform. That will be very, very soon. Yeah.
I have a question for you guys. How do you manage your SCADA data on the back end? How do you, I mean, given that a lot of folks have existing SCADA sensors, how do you actually make those connections? How do you deal with security? How do you give it access to the organization? Things like that.
Yeah, that's a very good question. So obviously what we tend to do is this platform is installed in the servers of our clients, because a lot of people feel that they prefer to have all these systems protected under their existing cybersecurity policies. So this is a software that will be installed in their servers and under all the protections that they've got. And the only thing they need is they need to talk to the SCADA data. They don't modify the data. They just copy the SCADA data. So we've got some connectors that we can do here. So obviously we got them for flow, for pressure, and then we also have for smart meters. So if you've got a big industrial consumer that might be distorting the results of the network depending on how they consume, we could connect to them as well. And it's as simple as for each of them add a connector. We've developed files, SQL databases, and also web services. This is the three we've so far met when we've been implementing the software in different countries. If you were giving us a different type of connection that we've never seen before, it would be a matter of just developing a new connector. And then that will help you to connect to whatever database. You can have the password. You can put here a little query to extract the data, and that will be bringing automatically the data without the need to modify it or anything. So it's just copying that data. So you will need to have a window or the SCADA data, which usually is very protected, will need to be able to send that data somewhere inside of the system of the company. And then our platform can read that from whatever means they are allowed to, and protect it under the cybersecurity system. Alex, I'm not sure if you want to add anything there, because that's probably...
No, I think you covered it perfectly. Yes, this is a concept. We are simply interrogating existing data set and importing to our database. So it boils down to a connector. A connector that we have three types so far, but if we come across a new format, we will need to develop a new connector.
Yep. The software could go also on a cloud system, but so far we've never found any gas utility that is happy with their data to go to cloud providers. They think it's very sensitive. I'm not sure, maybe in the US it's different because some of the cloud providers are US companies, but when we work abroad, overseas in other countries, they don't like their data to be in servers that are not physically in their country.
If anyone is open to open up their mic, if there was anything that you wanted to add while we have Alex and Juan, or also feel free to put it in the chat.
One thing maybe, Scott, we should say is we are focusing on gas modeling tools today, but as you might remember from my presentation, we traditionally come from the water sector. We do have other number of tools for water systems. I know some of you guys are water modelers, and we've got tools for leakage detection in water supply systems, and we are planning to do something similar to Simon gas operation in the water sector. We haven't decided yet exactly how to do it, but it will be very, very similar probably to the way we've done it. Alex is showing you an image of Simon Water. I would invite you to visit our website. We've got more information there, and there are some brochures and some YouTube videos. And then if any question arises, or like Clint was saying, any ideas of future collaboration, we are happy to look at that. Tom is saying,
we do have a question from Tom.
Yeah.
Sorry, Kendall. Says, I'm a water modeler, but this is definitely interesting user interface. As the model gets larger, how much does the internet connection slow down?
Alex, I'll let you answer that one.
It's not much about the interconnection. It's about the data. I think it's about the rendering sometimes. As the model grows bigger, there are sometimes, but I never found that annoying. A bit of time to generate the rendering the image. Yeah, that maybe has an element of internet connection. But I never seen any situation which was creating problems.
Yeah, the problem we've seen is when we are maybe VPNing, using a VPN connection to connect to a client in Chile or in Taiwan or somewhere like that, and the band is not very good, each of the ends, and then the rendering doesn't work very, very well. But when we are working, like this is meant to be used, like inside of this intranet system of a utility, where you have a very good connection to your own system because you are inside of the same network, it tends to work very fast. We've never seen any problem with big models. We've tested models 60,000 pipes, 80,000 pipes, Alex, in some of the clients in Italy, and they work fine.
I think it was even more, 80,000 pipe and 500,000 customers.
Yeah. Our idea is to develop something similar to Simon gas operations for water, probably using the IPANET engine, no, Alex? We're still considering different.
I think we need to use this because it's quite standard in many countries. Yeah, it's quite fast, so probably IPANET would be the choice.
Yep.
That does bring us to the hour. I'm sure Alex and Juan are happy to field any other questions,
Of course.
but that was our scheduled time. I really appreciate everyone joining, and especially Alex and Juan.
No problem.
Thank you very much. Okay.
Yep.
Have a nice
Thank you very
evening.
much.
At least here in Italy's evening. Okay. Thank you, Scott, for organizing this.